So in addition to what we did last time, which was went over the basic probability rules, we do have an addition rule, which is funny because I said in addition to, there's an addition rule. I'm funny. The addition rule and complements is what we're going over today. The addition rule is really for statements that I'm going to call or statements. If you're doing some sort of probability and you're talking about you could have this or that, you're using the addition rule, which tells you what to do with those probabilities. You're going to add them. But before we get there, we need to talk about a vocabulary word called disjoint events. Two events are called disjoint if they have no outcomes in common. You'll hear me call them mutually exclusive because that's another way to talk about disjoint events. That means that if we were looking at a Venn diagram of event E and a Venn diagram of event F, you see how these Venn diagrams, it's actually not a Venn diagram because they don't overlap at all. That means that event E and event F are disjoint. They have no overlap, nothing in common. If we are trying to find the probability of two disjoint events occurring, meaning we're trying to see if either E or F will occur and they are disjoint, then simply all we have to do is add the probabilities together for E and F separately. Now, I can't help it. The book uses the word or in the middle here. However, there is a different notation that you will see me accidentally write down, and or if you Google around for help on the internet, you're going to see this symbol. Do y'all remember this from college algebra? It was the union symbol, right? It technically is the word or in mathematics. So if you see me put the U, I'm meaning the word or. And that's what we meant in college algebra when we did intervals, this or that. It was the word or. Okay, we're going to just jump right into an example. Example 1 called Benford's Law. Our number system consists of the digits 1 through 9 because we do not write numbers such as 12 as 0, 1, 2. The first significant digit in any number must be 1 or 1 through 9. We may think that each digit appears with equal frequency so that each digit has a 1/9 probability of being the first significant digit, but that is not true. In 1881, Simon Newcomb discovered that digits do not occur with equal frequency. The physicist Frank Benford discovered the same result in 1938, and after studying lots and lots of data, he assigned some results for the possible occurrences of each data shown in the table below. This is called Benford's Law and plays a major role in identifying fraudulent data on tax returns or accounting books. So, we're going to do a few things with this table. The first thing we're going to do is verify that Benford's Law is an actual probability model. There were 2 rules last time we learned to convince ourselves that something is actually a probability model. Do you remember what that first rule was? No, but you're on the right idea of something being less than something.
Less than 5%.
No, that would be an unusual occurrence. That's what you're remembering. Well, what I was looking for is that all of the probabilities in the model are between 0 and 1. So if we look at all of these probabilities, are they all bigger than 0?
Yeah.
Are they all smaller than 1?
Yeah.
Yes, so we're good. So all of the values in this probability model, that looks super weird. Let me write that word again. All of these probability models are between 0 and 1. The second rule, does anyone remember that one? When we add them all up, they need to equal 1. So let's do the sum really quickly of all of these numbers. 0.301 plus 0.176. You get it. If we add up all of these probabilities, what do we get?
1.
We get 1, which is what we wanted. To confirm that it's a probability model, they should all add up to 1. So we're good. This is a true probability model. Now, part B says to actually use Benford's Law, so use the table, to determine the probability that a randomly selected digit is 1 or 2. So we're going to have the probability of both 1 and 2. If we are finding the probability that event 1 or the event 2, which is like event E and event F, occur, we can do this separately as the probability of 1 plus the probability of 2. We can do them separately because these are disjoint events. There is no overlap between 1 and 2 because they're completely separate things. They're disjoint. They're mutually exclusive. So if we look at the table, The probability of 1 is 0.301, and the probability of 2 is 0.176. So all we have to do is add those two numbers together. 0.301 plus 0.176. Therefore, the probability that either the first number in a randomly selected, the probability that a randomly selected first digit is 1 or 2 is 0.477. We just simply add them together. We can also extend this addition rule to more than just two things. So if I was looking to see the probability that a randomly selected first digit is at least 6, that means I'm looking to see if it is 6, 7, 8, or 9. Those are all at least 6. So the probability that we are looking for something that is at least 6 will be the probability that is 6 plus the probability that it is 7 plus the probability that is 8 plus the probability that it is 9, because those are all disjoint events. They can't occur at the same time. So we just simply take all of those probabilities from the table, which would be 0.067 plus 0.058 plus 0.051 plus 0.046. And if you trust my math, which I know some of you do not, which is fair, you get 0.222, which means it's a 22% chance that the starting digit of a number is larger than 6, at least 6. I guess I should say 6 or larger. So again, this is for disjoint events, events that don't have any overlap if we were making them into a Venn diagram. A classic example that we like to use in probability, we did do this, we started to do this last time, I think, is to think about a deck of cards or maybe rolling a die. So on our next example, we're going to be looking at a deck of cards. And just in case, I think you guys all play cards, right? How many cards are in a deck typically? 52. And there's 4 suits. There are 4 face cards. Or, yeah.
3 face cards.
Well, if you consider the ace a face card. Depending on what game you're playing. Ace can be high or low, but whatever. Okay, so here is our set of 52 cards in a deck. So this is my sample space here. That means this represents S. How many items are in my sample space? 52. Okay, so those are two things we know from the sample space of a deck of cards. If I was randomly dealt one card, there's 52 options that it could be. So we're going to compute the probability of event E, where E is drawing a king. So let's highlight with our I'm using pink, our pink highlighter here, all of the kings, which is this entire column. How many individual events did I highlight? 4. So if we're finding the probability of E, where E is drawing a king, the formula would be, from last time, the number of times E occurs over the number of items in my sample space. You guys just told me that there are 4 kings out of the entire sample space of 52 cards. 4 over 52 means I have a 1 in 13th chance of randomly drawing a king from one card. Now, does that make logical sense to us? There's 4 kings in a deck of 52, so we have a 1 in 13 chance of getting a king. Now, if we do multiple events at a time, that's what we did last class, part A, but part B is more than one event occurring. So E is still going to be drawing a king, but this time F is going to represent drawing a queen, and G is going to represent drawing a jack. So if we highlight our sample space to kind of reflect this, F would be all of the queens, and green for me would be all of the jacks. If we're trying to find the probability that we will get a king or a queen or a jack, notice the emphasis on the word or, That means that all we have to do is add together their separate probabilities. These are not overlapping events. A queen cannot also be a king. A jack cannot also be a king in a deck of cards. So we know that the probability that we will get event E or event F or event G. Remember, you can use the word or in place of the union symbol that I'm using. I just can't help myself. Would be separately each individual probability. So we will do the number of kings over the sample space plus the number of queens over the sample space plus the number of jacks over the number in the sample space. And since they're all disjoint, there's no overlap, all we have to do is add together the probabilities or the numbers, which there are 4 kings out of 52. There are 4 queens out of 52. There are 4 jacks out of 52. Fraction rules means you just add the numerators. Don't add the denominators since they're all the common denominator, which means this will end up being 12 over 52, which does reduce down to 3/13. So we have a 3/13 chance of getting either a king, queen, or jack, which for some games are the only face cards if ace doesn't count as a face card, in pulling one of those cards. They're all disjoint events. But like, what happens if we're trying to find the probability of something occurring that are not disjoint events? We're going to use what's called the general addition rule to make this happen. So this time, unlike the Venn diagram from before, where the 2 circles were not overlapping at all, there's going to be some items in common. So let's go ahead and label this as maybe event E, and this one would be event F. We have this overlap. This overlap is called E and F, because that's when it's happening in both. That's the intersection. You're going to end up seeing me use an upside down U. Looks like an N to me for intersect. That's an overlap of my 2 events. So what do? Let's figure it out. It says, suppose we are randomly selecting chips from a bag, and not like chips like eating chips, but like things with numbers on them, okay, like chips. Okay, they're labeled 0 through 9, and we're going to let E represent the event that we are choosing an odd number. So let's go ahead and highlight all of the odd numbers in this list, like 1, 3, 5, 7, and 9. And we're going to let F represent the event choose a number less than or equal to 4. So I'm going to highlight in blue all of the numbers that are less than or equal to 4. Do you see how there are some numbers that I've highlighted in both colors? That is our overlap. That is what's happening in both events. So that's going to be a problem, because watch, if we were just to use the rule from last time, or sorry, if we're going to look at this classically, of the things I've highlighted, E or F, there is 1, 2, 3, 4, 5, 6, 7, 8 things highlighted, correct? So this would be 8 over 10, which is 4/5. That's the correct probability of this occurring. However, if I were to use the old formula, which just said to add up the individual probabilities, we're going to do the probability of the pink one happening. How many pink letter numbers did I highlight? 5 out of the 10. And if F is my blue highlighting, the numbers that are less than or equal to 4, how many blue numbers did I highlight? 5. What's 5 over 10 plus 5 over 10?
1.
Yeah, 10 over 10 or 1. Can that ever happen? That means with certainty we will have one of these 2 events happening. And we know that's not true because 6 and 8 are even numbers that are not less than 4. Like, we didn't highlight those. So this is a problem. So we have to adjust our formula. Instead of just adding up the probabilities, because we know that doesn't work, we're going to add up the original probabilities, the probability of E and the probability of F, but then we're going to subtract this overlap. We're going to subtract any of the overlap, which is exactly that middle of the Venn diagram where I've double highlighted them. So if this was the formula I'm using, we'd go back to what we did before, which was 5 out of 10 plus 5 out of 10. But how many numbers did I highlight in both colors? 1 and 3 have both colors, yes? So we're going to subtract those 2 out of 10, the overlap. 5 plus 5 is 10, minus 2 is 8. This is 8 over 10, which agrees with the classical probability we know from just thinking about this problem to begin with. Now, this is an oversimplified problem, so where you're like, well, duh, it's 8 out of 10. I get it, but when the events get more complicated and they are not disjoint, they are not mutually exclusive, we have to subtract the overlap, which means that our general addition rule, the rule I'd prefer you to memorize, is this rule here, that if we are doing the addition rule or the OR statement for any event, we are going to take the probability of the first event plus the probability of the second event minus the probability that they overlap. This works regularly because if they are disjoint, there is 0 overlap, and so you'd be subtracting 0. So this is the general rule that we'll use for either disjoint or non-disjoint events. It's just that for disjoint events, you're subtracting 0, so it doesn't matter. Can I show you what an example looks like of this rule? We're back to the cards, though. Here's our sample set of the deck of cards. This time, we're going to compute the probability that we're handed a card, and it is either a king or a diamond. Okay. So we know this. Drawing a king is this last row. But then drawing a diamond is the whole thing. I said row when I meant column, right? Oops. You get it. So if I highlight all of the diamonds, do you see how there's like now an overlap between these two events? This is no longer disjoint. We actually have a physical overlap when we color it like this, but also we know there is a king that is a diamond. So when we do the probability of this OR statement, the probability that we get either a king or a diamond will be the probability that we pull a king plus the probability that we pull a diamond minus the probability that we pull a diamond that's a king. So this will look like this. Probability of E plus the probability of F minus the probability of E and F. So they're happening at the same time. If we look at our sample space, again, the number of things in my sample space is 52 because it's a deck of cards. So this will be 4 out of 52 plus how many out of 52? 13 out of 52. That's all the diamonds. Minus how many overlap? 1. There's one card that is in both a diamond and a king. 14 4 plus 13 is 17 minus 1. This is 16 over 52, which reduces to 4 over 13. So we have a 4 over 13th chance of somebody handing us a card and it's either a diamond or a king. We have to remember that for these non-disjoint events, when they have things in common, that we would be double counting the diamond king unless we got rid of one of them. That's what we're doing, is we're getting rid of the fact that we would double count that diamond king on both the diamond count and the king count. We're getting rid of one of the overlap. Yes? Questions? Okay. Another something you'll see a lot when it comes to probability is these contingency or two-way tables. Our book calls them contingency tables, but if you took geometry class recently, we called them two-way tables in that class. Same vibe. A contingency table or a two-way table relates two categories of data with both a row variable and a column variable. Each box inside the table is called a cell. So really, and don't do this on yours because you're going to be annoyed, this is actually the table of information. We have columns for males and females, and we have rows that represent their marital status. The last row and column is a total of that row or column. So when we made this, and you might have to make your own total row, which is why I'm telling you this, we added these two numbers to get the total number of people never married, not depending on their gender. We added all of these up to see the total number of males, not depending on their marital status. So these two-way tables tell us a lot of information. You may have to do the totaling yourself on a particular problem, so just be ready for that. The first problem we're doing here says determine the probability that a randomly selected U.S. resident is male. All right, here's our first thing. A randomly selected U.S. resident is male. So we are literally just trying to see the chances that we would pull that number instead of this number. So we look at the total on that row. The total on that row, the total number of people, male or female, that we've surveyed in this marital status information from the U.S. Census is 260.1. So if we're finding the probability of event E that we randomly select somebody who's male, it will be that 126.9 over 260.1. And if you trust me to do that math, it's 0.488. So 48% chance that we just randomly pluck a dude. The second part says, determine the probability that a randomly selected U.S. resident is widowed. Okay, so we look at our table for widowed. And if we're selecting if we're randomly selecting somebody, there's this many people, male or female, that are widowed from this survey. So if we were looking for that probability, the probability of, let's say, F is being widowed would just be that 15.2 over the total number in the survey. And if you trust my math, that's 0.058. That's just regular probability, right? One event occurring. The next two examples, we're going to have two events occurring at the same time. Part C wants me to find the probability that a randomly selected U.S. resident is widowed or is divorced. Now let's think about this for a second. Is there any overlap of somebody who's widowed versus divorced from this table? Do I have a row that says widowed and divorced?
Yes.
I do?
Oh, no? A row?
A row that says widowed or divorced.
Oh, no.
No, I have a row for widowed and I have a row for divorced. Based on this, we can't be both. I know in real life you can make all these if statements if they were. After lunch, we'll finish this problem. This is going to be a disjoint event. When we left for lunch, we were working on this problem, and I already forgot what it was, so let's reread. We're determining the probability that a randomly selected U.S. resident is widowed or divorced. So we were talking about making a decision whether this is disjoint or non-disjoint. Are there any, by this table, widowed and divorced people?
Well, they're separate, but they're not like together.
Great, so it's disjoint. Based on this table, the only overlap we're going to have is between gender and marital status. Okay, so if we're looking at this, the widowed, we already have 15.2. Divorced is 28.2. So if we're looking for the probability that somebody would be either widowed or divorced, we would do the probability of, this will be F, or divorced, we'll let divorced be G, would be the probability of F, which is 15.2 over that 260.1 plus the 28.2 over the 260.1. when we do this math, we would get 43.4 over 260.1, which if we change to a decimal is 0.167. So we didn't have to subtract any overlap because there is no overlap between widowed and divorced. They're both rows, not a row and a column. However, if we look at, let's write down that this is disjoint for ourselves so we remember why we didn't subtract. If we look at the last problem though, it says determine the probability that a randomly selected U.S. resident is male or widowed. Now in this case, if we look at the male number and we look at the widowed number, is there an overlap between male and widowed? Yeah, we do have an overlap. There's this overlap right here of males who are widowed, or widowed people who are males.
Does it always say or would it be situation or would it be and?
And we will learn about and in like 1 or 2 lessons. So it's a completely different rule when we do and, which is why I'm emphasizing the or so much.
Oh, okay.
Yeah. Good question. Is the intersection, yeah, of when they're alike, but when we're just solving an and with no other information, it'll be a different formula. Good question. If we're doing this one, so this one is going to be the probability of E or F. We will have to do the subtracting because we want to do the probability of E, which is 126.9 over 260.1, plus the probability that we are widowed, which is that 15.2, and then we're going to subtract the overlap, which is 3.3 over 260.1, because that's what we have double counted if we're counting both the males and the widowed row. When we do that numerator, so 126.9 plus 15.2 minus 13.3, we would get 138.8 over 260.1, which as a decimal is 0.534. So when it's not disjoint, meaning there is an overlap between them, we have to subtract away the overlap. So these are not mutually exclusive events. The last rule we're going over today, it's not the last probability rule, but the last rule is called the complement rule. Suppose that our probability of an event E is known, and we would like to determine the probability that E does not occur. Give that not a big ol' underline. This can easily be accomplished through the idea of complements. So the notation for complement is kind of interesting, and the concept of complements feels like really straightforward, and it is. Don't let it get too complicated. Let S denote the sample space of a probability experiment. So this box represents all of the options for us in this probability experiment. Let E denote an event. So here's E. The complement of E, which we would write as E to the C power, is all outcomes in the sample space that are not outcomes in the event E. So if this is the whole sample space and this is E, literally everything outside of that circle is E complement. So everything that we could possibly get, if this bit is the event E, everything else besides the event E is E complement, not E.
So we're seeing what we're not getting.
Yeah. Okay. Now the complement rule is really quite simple. It makes a lot of sense. We would say that the probability that E complement will occur is equal to 1 minus the probability that E does occur, which makes sense. Probability has to add up to 1. So E and E complement should add up to 1. So if we solve that for E complement, we're just subtracting the probability of E. It is as simple as it feels. Okay? In example 5, according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? Here's what we know. We know the probability of playing the lotto is 0.52. So the probability of not playing the lotto, meaning literally everybody who did not play the lottery, would be 1 minus the probability that you did play the lottery, So that's 1 minus 0.52, which is 0.48. And that makes sense, because if 52% did play the lottery, everybody else did not. So that's a complement. It is that simple. Okay? If we add this into problems like we've done before, the data in table 7, this is example 6, represent the income distribution of households in the United States in 2017. We're going to first compute the probability that a randomly selected household earned $200,000 or more. Okay, $200,000 or more. Let's see from our table, what is the number of households that did earn $200,000 or more?
8,200.
Fabulous. So to be able to really do these probabilities, we do need to know the number of homes in our sample space. So we're going to go ahead and say if this is our sample space, these are all the people who we surveyed. The total number I would get by adding up all of the homes, all of the numbers in thousands. So it's, just to fast forward, it's 120,063 when we add up all of those numbers. So to find the probability that event E, which is earning $200,000 or more, occurs, will be that 8284 over the 120,063. If we calculate that real quick on our calculator, we get 0.069. Let's say now that we want to figure out the probability that we have, we pick a household that has earned just straight up less than $200,000. So everything else. So you have two ways to do this. You could take the long way, which is adding up all of those numbers and then doing the probability there, or realizing the probability of us getting less than $200,000 or choosing a family is the same as 1 minus the probability that we did choose, because it's everybody else. So this idea of complements can sometimes speed up our processes because we don't have to add all those numbers together, especially if our data was like ginormic. That would be annoying. So we can use the idea of complements. So we're doing 1 minus 0.069, which if we fast forward is 0.931 or 93%. Our last question here says that what is the probability that we would choose a family that has at least $10,000? Well, all of the things that earn at least $10,000, I'm going to highlight in blue. That's this one, 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 and this one. It would be kind of annoying, especially if this data was even larger than this, to add up all of those numbers and then do the probability. So instead, do you see that there is only one category that I did not choose?
Yes, so that's not.
Yeah, so if we wanted to see the probability that we earned at least $10,000, we can compute that as the complement of, or 1 minus, the probability that we earned less than $10,000, which is a category we can see on our table. Which would mean I'm doing 1 minus 7804 over the total number, 120,063. We calculate on a calculator, beep boop bop, we would get 0.935. So for a lot of problems, the idea of complements just speeds up our processes. Again, you totally could have added up all of those numbers. The categories we highlighted in blue, could added them all up, divide by the total number, we'd get the same probability. But this could just be faster or more accurate so that we don't like make a typo.
There are two left
So like, that's a great question. So if it was asking like, how about less than 1,500? Well, that's everything but these two. So yes, you would do 1 minus this minus that.
To get the number
Or
first.
add them up and subtract them. Yeah, I subtracted them separately, but add them together and subtract them. Yes, you totally could do that. So you can use probability complements to make numbers and computations easier. Sound good? Next class, we will add in the probability of and statements. So we're going to work on those and statements as opposed to the or statements that we did today. Today is all about or, either disjoint or not mutually exclusive events. That's what we worked on. And then complements, of course.